let's focus on some radioactivity for chapter 21 and nuclear chemistry. First thing we want to establish is what the hell is radioactivity? By definition, it is the emission of subatomic particles or high energy electromagnetic radiation, in other words, gamma rays, by the nuclei of radioactive elements. And not every element is radioactive. Only the heavier ones are radioactive isotopes, but are all radioactive. But some of them, lighter, do have radioactive isotopes. So radioactivity as a phenomenon, think about it this way. And we're going to talk about this probably next week because we won't have time this week. Is you have the nucleus. You have positives and you have neutrals in the nucleus, right? Not a negative. It looks like a negative, but it's a neutral. Neutrons. For something like lithium, right? Lithium has 3 protons, and the atomic mass is 7, right? The average atomic mass is 6.941. This means that the most stable isotope, the most abundant isotope, is 7. So the nuclides is a term meaning for we call them nucleons. A nucleon is either a proton or a neutron. They call them nucleons collectively. So the number of nucleons is 7, and 3 of them are protons on average. So we'll put the other 4 as neutrons. This is what we call the happy zone, or the zone of stability between protons and neutrons. And we'll talk about that ratio later on. What happens when radioactivity happens is the ratio between protons and neutrons gets out of whack. Meaning if you stuff in there a bunch of neutrons, what's going to happen? They're going to be super crowded. The protons might be forced together, which creates repulsion and stronger repulsion over time. Time is very important here because over a certain amount of time, that time is the half-life, the force of the internal particles on each other, the repulsive forces of the protons, will be enough to shatter the nucleus and break the nuclear barrier. This nuclear barrier isn't like a ball pit, or it isn't a defined solid structure. It's a force. We call it the strong force or the nuclear force. Once that force is broken by the internal repulsion forces of the protons, we get radioactivity. And what happens? Oh, look, particles from the nucleus are emitted everywhere. So we have neutrons are going. We have protons sometimes are going. We have alpha particles, beta particles, and things like that. So that's what radiation is. This process happens where the nuclear barrier's force becomes overcome by the repulsive forces inside the nucleus, which eventually leads to the nucleus exploding and releasing particles. Another way is instead of too many neutrons, you can have not enough neutrons. So imagine if you had no neutrons here. Let's just try to blank them out. You would have 3 protons bouncing against the walls. Every time they come in contact with each other, they bounce off faster because they repel. Then they come in contact again, they bounce off even faster and faster and faster and faster until it creates a force that's too much, and then the same thing happens. So the neutrons have a happy zone, not a million, not 0, but for lithium, it's like 4. That's where the neutrons create a sufficient buffer between the protons to where they can live in happiness. So that's what radiation is. Any questions on that? No? Okay. So radiation and radioactive isotopes are used in a lot of different things. We're going to talk about carbon dating, geological sample dating, medical applications, nuclear bombs. Hopefully not anymore, but we have them. But hopefully no one does something stupid. And also energy. Energy is probably the way it should be used the most. Well, nuclear medicine's all right too, but like radiation therapy for cancer, not a fan. Oh, we were speaking of cancer before. The best cure for cancer is surgery, if anybody wants to know. If someone asks you like, oh, what's the best cure for cancer? So surgery has like a, depending on which type of cancer and which stage, overall has like a 70 or 80% success rate in terms of the person going into remission afterwards, because you're physically taking the tumor out. It's better than any chemotherapy, better than any radiation, but it's surgery. If you have a brain tumor, surgery is very difficult to do, which is why people like me are hopefully going to be employed and can continue to work on research to develop certain drugs that can modulate tumors and not modulate, but decrease the size of tumors in tough to reach areas. And yeah, you're right, Christina. Skin cancer is very easy to get rid of if you were in early stages. Yeah, like I like probably a significant proportion of older people that we know have probably had one removed. I think my mom has. That was like a pre-cancer benign thing. And my grandparents all have had one removed, and it's common. So here we go. Isotopes. So isotope notation. We have this new symbol. It's called the nuclear symbol. It is a little bit different. We've seen it before, I think, in Chem 1, but it's a little bit different than the periodic table symbol. We have the mass number on the top, the atomic number on the bottom. So this means if you have lithium, we have the chemical symbol for lithium. 7 is the mass number, and 3 is the atomic number. So what we can do is we've seen this in Chem 1, just to refresh. What we can do is we can just put a subtraction there and we get 4. And this means there's 4 neutrons. So that's very simple math that we can do. Okay, so now let's look at the different atomic symbols for the types of radiation that are going to be emitted. 3 of these we should have no problems with: proton, neutron, electron. Proton is normally P positive, neutron is N0, electron is E minus. Symbols: protons we know are H plus or just H11 or P11. Neutrons are 1, 0 because they have no protons, but they have a mass number of 1. Electrons have virtually no mass, and they're considered to be the opposite of a proton in terms of their proton number, meaning it's -1. The new ones, put them in red for danger, radioactive. We have alpha, beta, and positrons. So an alpha particle is the heaviest radioactive particle, or the heaviest the heaviest smaller radioactive particle out of the 4. And there are 4, 3 of them are shown here. One of them is out, and this is alpha particle. So we see 42A or 42He. So basically an alpha particle is a high energy helium atom that is emitted from a radioactive decay. Beta particle is basically a high energy electron. Same exact notation as electron. It's just emitted from a radioactive reaction. So you can put 0, -1b or 0, -1e. A positron is exactly what it sounds like. It is a positive beta particle. So it's a positively charged electron. And you might think, why the hell do we need that? There's this thing called positron emission where these can be emitted. And why would this be emitted? Because the positive charge from the proton is taken by an electron. And then the proton converts into a neutron. You'd be like, whoa, what the hell? Is that possible? Yes, it is. And we'll talk about that more later on. Okay, so conceptual question. How many protons and neutrons are in the isotope 2713 aluminum? Answer is D. 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 Yep, it's D. Yep, that's a brain fart. Okay. Protons are 3 or 13. So neutrons, but some people still had the wrong answer, so I do want to go over it. Okay. Yeah, this is going to be edited out. Cut. All right, so the mass number, so we know protons plus neutrons equals mass. So what we can do is do the mass minus the protons, which is 14, and that's the neutrons. So D is the answer. Oh, I can do that. Clap. Wait, okay, so I'm going to make an audio spike. Wow, Rebecca, you got some great ideas today. Wow. You're on the roll. And still jobless. No, I mean, I'm still in the job search too. Oh, that Army thing went well too, but it's still extremely early stages, so I'm still looking for other stuff. I mentioned it like a month ago. Okay, so types of radioactive decay. We have alpha decay and beta decay, and you have also gamma decay, which gamma rays, they weren't, this is the first time we're seeing them, right? So what a gamma ray is, we've seen it before in chapter 8. It's not a particle with mass. It's a form of light. It's electromagnetic radiation. We've seen it as, remember, it had a very high frequency. That's what a gamma ray is. So we have our beta particles can be emitted, our alpha particles can be emitted, and our gamma rays can be emitted. Not admitted, emitted. We can also emit positrons, or we can capture electrons. So I'm just throwing a lot of terms out there, but we're going to go over each one specifically after we go over what a nuclear equation looks like. So I guess for today, what we'll do is we'll go over all of the different types of decay, and we will cover the nuclear equations. Okay, so here's a nuclear equation. They are very simple to go over. All it represents, just like a normal chemical equation, is the conversion of one set of atoms to, or one set of compounds to another. But in this case, it's one set of elements to another. So we call them the parent nuclide and the daughter nuclide. You can just call them reactant and product. I don't really care, as long as you know left and right side. Now, what we can say is that for this alpha, this is called an alpha decay. Alpha decay of uranium-238, which is what happens in a nuclear fission plant. So what happens is in an alpha decay, and you know just from looking at uranium-238-92 that an alpha particle is going to be in the product. It comes out. So you're going to have 4,2 helium. What's left in terms of the mass and in terms of the protons? Because we have to conserve the mass and protons on the left and the right side. So both of these numbers have to add up on the top and on the bottom to the ones on the left. So we have our helium is 4. To get to 238, we need 234. And then we have 92 and 2. To get to 92 from 2, we need 90. So our answer is going to be 234, 90. Then you can look at the periodic table and take a look. What's 90? Oh, it's thorium. And look at that. We got thorium or thallium. Thallium. Thorium sounds cooler, but I think it's thallium. Okay. Any questions on that? No, thallium might be TL. So it might be thorium. Thallium. I think it's thallium. I don't know. Those heavy elements I don't really care about. Even as a chem professor, I don't memorize the whole table. But anyway, any questions on that? No? Okay. So we've seen alpha decay. That's the first type of equation. So you're emitting one of these alpha particles, which you can write 4,2 helium, or you can write 4,2 alpha. Both are acceptable. And they come from uranium. So here's an example. So you have an alpha decay. The nucleus emits a particle composed of 2 protons and 2 neutrons, which is helium-4. And it just comes out because the radiation or the internal, what we call strong forces, are overtaken by the internal nuclear forces. Okay, there's two other phenomena that we can talk about with these different types of decays. And the first is ionizing power. Now, what ionizing power is, it's the power of a radioactive particle to ionize other types of molecules. And we also want to talk about penetrating power. Now, penetrating power has to do with how lethal is the type of radiation emitted, meaning how many layers of clothing can it go through, or how many cinder blocks can it go through. With gamma rays, we know they're in the Chernobyl, they're in any nuclear reactor. When it has a meltdown, they're very dangerous. They can go for miles, hundreds of miles in every direction and damage DNA and do a whole bunch of bad stuff. They have very high penetrating power, but low ionizability. Now, the ionizing power, alpha radiation, so alpha particles have the highest ionizing power, but they have the lowest penetrating power. So they're usually inverses. Beta decay is the next one where we're going to see the equation for right here. Beta decay basically means the emission of a high energy electron, right? We learned a beta particle is basically the same thing as an electron. So we use this fancy B, 0, -1, beta decay. So what happens is, it says here, occurs when an unstable nucleus emits an electron. Yeah, that happens based on the equation, right? But do you want to know what really happens? What really happens is that you see this radium goes from 88, becomes actinium at 89. But the masses stay the same, and that makes sense based on the equation. The electron that's emitted doesn't weigh anything. But a proton was gained. How's that possible? And the answer is, a neutron was converted to a proton. Yes, good job, Christina. Yeah, so a neutron was converted into a proton. Now, how's that possible? Well, sometimes this neutron to proton ratio that I talked about before can get out of whack, and the most energetically favorable way to restore its stability is to turn a neutron into a proton if there are too many neutrons in the ratio or in the nucleus. It kind of restores the balance a little bit. How does it do that? So the neutron, I mean, this is where you get into like quarks and stuff, but the neutron is composed of a positive element and a negative element, and then like some other subatomic crap. I don't really know what it is. Some like quarks and bosons and stuff, right? So what happens is one of those one of those subatomic particles will come out. And why does it come out? Because of energetic favorability. You know, like kind of like why two hydrogens bond together, because their product is more energetically stable than the reactants. And yes, then the electron, the negative part of the neutron, is then emitted. So then without the negative part of the neutron, what's left over? Just the positive part and some other stuff. So that's basically a proton. And that's why the protons increase. Now, if you want to take it a step further, you can say, all right, what's that other stuff? And why isn't that, like, what is that? Well, it's these very, very small particles. And how do we know they're there is we actually know this from Chem 1. When we went over the mass of the neutron and the proton and the electron, maybe to my, I'm not sure which lectures you were in, but to my class, I always said that, don't you notice how if you add up, we would always say the mass of the neutron is about the same as the proton and the electron's basically nothing. But in Chem 1, I say that, but now that's not a relevant thing to say anymore, because if you add up the mass of a proton, which is 1.007 AMU, you add up an electron, 0.0055, what do you get? 1.00755. That's a proton and an electron put together. Now, what's the mass of a neutron? 1.008. Well, there's some missing mass there. So there's two reasons for this. One, because there's more stuff. There's like little tiny things. And two, because of this thing called the mass defect, which we'll talk about later, is that when these reactions actually occur, some mass is released. So to get from a neutron, 1.008, to a one proton, 1.0075, or so to get to, sorry, not even that, to get to 1.007, because it goes from a neutron to a proton, releases the electron. The gap, there's still a gap between those. And that gap, that mass that is missing becomes energy and is released as energy in this process. And oh, guess what that means? How do you calculate how much energy that is? Oh, E equals mc squared. Boom. That's exactly how to do it. That's what the mass defect is. E equals mc squared. Because these particles are moving at the speed of light. Or very close to it. Okay, cool. So now, that's beta decay for you. So here we go. In beta decay, a neutron becomes a proton, and the electron is emitted. So that's basically what I just said. Gamma emission. This is the high energy one that kills people. It causes cancer. It's bad. Least ionizing, but most penetrating. And there's no charge and there's no change to any of the top or bottom numbers because it's a radioactive part, or it's an electromagnetic particle and wave. So it's light. It acts as a particle and a wave at the same time. It's like an X-ray, but worse. And it could be emitted too. And it has energy, right? And we can calculate the energy of a gamma particle using our energy of a photon equation. Remember that one? E equals N. And then Planck's constant times the frequency. That's the energy of the photon equation. So that can be used to figure out the energy emitted by a gamma ray. And that energy came from the mass of the uranium. So this energy released is as a gamma particle. That's part of the mass defect. Even though a gamma particle is massless, that mass of the uranium was converted into energy to give it kinetic energy. This stuff's crazy. All right. Here we go. If the room next door contains an alpha emitter, a beta emitter, and a gamma emitter with all similar activities, which particles are you most likely to detect in the room you are in? Anybody? C, yep, gamma rays. Good. Because they're the strongest penetrating. And here's a little picture of that. So gamma rays could even go through some lead. So that's why with any nuclear reactors, they usually block it up with lead and concrete. And usually multiple feet of it. All right, positron emission. So this is the last one. And then we'll probably go after this. Or an electron capture. So positron emission, it is kind of the same thing. You emit a positron. So let's say you have phosphorus, which is at different, phosphorus 30 is a little bit radioactive. And during its positron emission, what happens? It releases a positive charge. And look what happens to the proton number. It decreases. So think about this. This is one of the main concepts. An island off the... Oh, yeah, that's where Godzilla happened. That's where Godzilla was made. You know, Godzilla is real. No, I'm kidding. But yeah, you're right. There was. I'm not sure of the details of that. Yeah. Okay. And also there was the Fukushima disaster. That was recently, or kind of recently compared to Chernobyl. But anyway, so in this positron emission, think about what's happening. And here's one of the key concepts. In beta decay, you're going from converting a neutron to a proton by releasing the negative part of a neutron. Now you're releasing the positive part from the proton and becoming a neutron. So you're going from proton to neutron here, right? The mass doesn't change. The proton number decreases. That means one of these 15 becomes one of these other 15. And now it becomes 16 neutrons. Right. So that's the opposite of a beta decay, is a proton emission. So here we go. In a positron emission, did I say proton emission? I meant positron emission. In a positron emission, a proton becomes a neutron, and a positron is emitted. Now, another way that the same thing can happen is by electron capture. So just to bring it full circle, positron emission, you're emitting a positive. Electron capture, you're taking in a negative. Same thing. It does the same thing to the product, but you are accepting a negative charge to a proton to turn it into a neutron. So instead of removing the positive from a proton, you're adding a negative. So literally the same thing. When a proton combines with an electron to make a neutron. I don't know why. Where does this electron go? I don't know why he's there alone. He's just floating around. Oh, here's what was I going to say? Oh, Heisenberg uncertainty principle. Watch. You see it in action. You see the electron? Oh, you can see its speed? Yeah. Well, it's gone. You don't know where it is anymore because you can't know its momentum and its position at the same time. Boom. Okay. So decay modes. Here's all of the decays. So we have alpha decay, beta decay, gamma decay, positron emission, electron capture. Those are the main three. Or not me. Those are the main three. Those are the main five. All right. Are there any questions on them? And I would say, in terms of what you need to know for exams, I would say memorize the symbols for all of the radioactive particles and just know how to use them in equations. If you see techneti, or let's say like phosphorus 30 goes through positron emission, write the equation. You should be able to do that. Because, okay, quick, what's phosphorus 30? I know phosphorus has an atomic number of 15, so it's 30-15. I know a positron is being emitted, so then the right side has to have a positron. And then doing the math, I can figure out what other element is there. So basically filling in the blanks for these different nuclear reactions. Would you guys feel comfortable doing that? Is there any questions on things you may find difficult, or does that seem pretty straightforward? Good. All right. So to finish off for today, what causes radiation? And we talked about this in the beginning, and we're coming back to it now, is that the nucleus is held together by this nuclear force. The nuclear force can be overridden by the internal force of the protons and neutrons based on throwing off the ratio between protons and neutrons, either having too many neutrons or too little neutrons in an element. So lithium, again, likes to have 4 neutrons. If it had 20, radioactive, because it wouldn't last. And the nuclear force is way too weak to keep all of the nucleons, protons and neutrons, in the nucleus. So, or you have too little, and then you have the repulsion of the protons will be too much, will create too much force over time. So more in next week, we'll talk about this N over Z ratio. The N over Z ratio, well, actually, let's go over it now. Yeah, let's go over it now. So the N over Z ratio, just to leave you on this note, which is important for next week, is this ratio. So we can actually quantify this ratio instead of just saying, oh, okay, if it's too little or too much, it's the neutron to proton ratio. And Z, we've seen Z before used for atomic number. So that means proton, and N clearly means neutron. So from the N over Z ratio, you can actually determine what the radioactive element is going to do, or radioactive isotope is going to do. If N over Z is too high and it's not stable, the neutrons are converted to protons in order to lower it by beta decay. If the N over Z ratio is too low, meaning there's too many protons, the protons will be converted to neutrons like we saw in either positron emission or electron capture. Now, this stuff does take some time to keep reiterating. So rewind and replay this part because that's important. So also in this little writing here, I say the neutron-proton ratio decreases during beta decay. So if it's too high, we want it to get lower. How do we get it lower? Decreasing neutrons by increasing protons. So converting from neutrons to protons. Because we can't change the mass. We just have to go from one to the other. And then the opposite is true for if N over Z is too low, we have to increase it. How do we increase it? Get rid of the protons, add to the neutrons. How do we do that? Positron emission or electron capture. And here's exactly this valley of stability, we call it. This yellow kind of segment shows which isotopes, based on all the different isotopes that we know, are stable and what combination of neutrons and protons they have. So let's do an example. If we have Rutherfordium. Rutherfordium has an atomic number of 44, it's right here, and a mass of 100. So that means the neutrons are going to be 56. That's why it's right here, right? It's stable. It's right on the green. If I encounter a Rutherfordium isotope that has a mass of 120, what's going to happen to it? How is it going to decay? That's an open-ended question to everybody to see if you were still listening. I'll say it again. If Rutherfordium, so Rutherfordium has 44 protons and it has 56 neutrons that add up to 100 as its mass. So this is Rutherfordium 100. If I encounter Rutherfordium 120, so 120 is like here, meaning it has 20 more neutrons, like right here, or even 40, whatever, just something in here. What's going to happen to it when it decays? What type of decay is it going to go through? So the N over Z ratio would be too high. What's going to happen? Good, beta decay, awesome. Yes, the neutrons will then, so what will happen is the neutrons will be lost. And when it decays, it'll go through beta decay, but in reality, it'll also go through alpha decay. And some of the mass will be lost too, because that's way too many. But in generality, to get back to this line of stability, we want to either convert the neutrons to protons or just get rid of them in the first place. So, yeah. And if the N over Z ratio was too low, we want to increase the neutrons, decrease the protons, so a positron emission will occur. Or electron capture. They do the same thing. There's some magic numbers, decay series, and we'll cover all of that. We'll start with this next week.